Hello everyone and welcome to We Meet at Digital Days. My name is Marie-Therese Kohl and I will moderate this presentation. We are very pleased that you took the time to participate in our virtual conference. The topic of this presentation is improving the EMI performance of isolated power modules. Our speaker is Timur Uludag. He will hold the presentation and will answer your questions at the end. But before we start, I would like to point out one thing. You will be muted during the presentation. This means that you cannot ask questions via microphone during the presentations. But nevertheless, you have the opportunity to ask questions during the presentation at any time via the chat function. And you will find the chat function in the control panel. This presentation will be about 30 minutes long. The chat questions will be answered in a Q&A session following the webinar. There are about 5 to 10 minutes in addition scheduled for this. And if we are unable to answer all your questions within this time, we will answer them via email afterwards. If you still have any other questions left, just mail us at exhibition@we-online.com and we will try to answer all your questions promptly. At the end of the webinar, you will be asked to participate in a feedback survey. We would be pleased if you take the time to fill out the survey and help us to improve the event. You will also receive the link to the presentation in the next few days, and the recording will be available at our website soon. But now I will hand over to our speaker, Timur, and I wish you an exciting presentation.
Thank you, Marie, for your introduction. I'm glad to take this opportunity. My name is Timur Uludag. I'm working as a Senior Technical Marketing Manager for the Magic Power Modules for Würth Electronics now since October 2015. Today, I will talk about isolated power modules, EMI performance, and how we can improve this. First, let's take a look on the agenda. Today, we will cover the following topics. We will start with an introduction about some myths around common mode noise. During the EMI basic section, we will summarize the needed EMI knowledge for the webinar. With this knowledge then, we can apply to the Kirchhoff's law to the common mode circuit. To prove that the rule of thumb works out fine, we will make a numerical example calculation for the Y-cap with one of our isolated power modules. To round off the topic, we show you the concept of predefined filters for our power modules. First, myth around EMI. When I ask some engineers about common mode, they always say, oh, common mode is very, very hard to understand. It's more like a try and error, and you need always common mode chokes. And as I mentioned, it's very hard to understand because it's very, very difficult. To be honest, that's completely wrong. The truth is that the suppression of EMI from common mode is not a rocket science. It's just using basic electrical facts and the Kirchhoff's law. But how can we do this? The same as we do it always. You need the right setup of tools and, let's say, a different point of view to EMI, and then it works out. To begin, let us first take a look on the application of an isolated power module. The isolated power module here in a typical industrial application is to interrupt unwanted ground loops and isolate from disturbances that can come from the DC bus. To understand common mode, you have to understand first that there are a lot of parasitics around involved. Here we have two simplified examples of real circuit construction. Example one on the left, if we have an input or an output cable, for a DC-DC converter, we will have two separate wires with different potential and a distance to each other. Therefore, we will have a parasitic coupling capacitance between them. Example 2 on the right. Also a single wire and a plane where we have different potentials and a distance will lead to a parasitic capacitance between them. To be better prepared for the next step, let us make a short wrap-up about the common mode and differential mode and its basics. The differential mode here flows in the same direction as the switching current. The common mode current flows on both supply lines in the same direction. The return path of the common mode current is the ground potential via the coupling capacitance. This is essential to understand. Please keep this in mind. The application from the beginning is only one of many applications for our isolated power modules. Therefore, it is nearly impossible to use one strategy for the common mode filter that applies to all. In order to ensure comparability, a standardized framework and experimental setup must be defined. Here, we use a structure based on CISPR 32 because this is sufficient here to be able to compare the effect of the different filter components with each other. The setup here shows the measurement of an evaluation board of an isolated power module. The structure of the power module itself have been expanded to include the components relevant to the common mode considerations. In the reality, the module is connected to ground on the primary side, for example, let's say minus V in. Then we will not have a balance, we have an unbalanced supply system. Also, the cable lengths in the reality are not defined to 80 centimeters or 100 centimeters. They are very, very shorter or can be longer. So this is an idealized setup where you can see all relevant parasitic elements that are included that have to be considered for the next steps to find the rule of thumb. The entire schematic can be now condensated to have a better understanding to a simple schematic as shown. We have here the source that generates the common mode noise, the path that passes them on, and the sinks that takes it up. The topology that is used for the SIP4 power modules is a self-oscillating push-pull converter. The switching action is driven by the saturation of the inductor current. The switching mechanism leads here to a certain dV by dt, which is the source of the common mode noise here. The detailed plot shows that the correlation is that we have got the switching itself that is named as first switching, and we have got the second that is the ringing. Both leads to the dV by dt. The noise current we're looking at is mainly driven by dV by dt, so we call it the capacitive effect. The effects by dE by dt will not be covered now because we're talking here about a low power device. First of all, a transformer is not a 100% barrier for the electric current. We always think that we have got some tapes and some wires and that there is a 100% barrier. But in reality, a transformer has always parasitic capacitance due to the primary and secondary winding structure and the resulting layer structure. These interwinding capacitance are formed between plus primary here and secondary, but also from minus primary to minus secondary. Due to the center tapped structure of the used transformer, we also have interwinding capacitance crossover. That means from plus primary side to minus secondary side, or from minus primary side to plus secondary side. In general, we have 3 different methods we can get rid of EMI noise, of common mode noise. The first is we can use some chip beat ferrites. Chip beat ferrites, due to its capability, only have a low attenuation for us. A bridging capacitor is there much better, but be aware if you use it for, let's say, an isolated converter where you have got a safety separation between primary and secondary, the Y cap we use, or you have to use, has to be safety proven. Or let's say one of the best parts, a common mode choke that suppresses all. A common mode choke can be used to get a very high attenuation, but it depends on the losses you want to have. If we now make a jump to the system level, then you can have 2 alternatives. You can use a snap ferrite or you can use a ferrite core. Let us now explore the meaning of don't let the noise reach the listen. The schematic here shows a simplified version of the setup we have already talked about. The schematic shows both noise current loops. As we already know, the common mode current flows through the power module and closes the current circle via ground, here marked with the red 2. The current loop, marked here with a blue 1, shows an alternative loop. The current flows through the power module and then takes a branch around the power module. But why should the noise current close the branch circuit? The branch has to be more attractive. The current always takes the easiest path, as we already know. That means the branch has to be less impedant than the existing one. If we take a look on the list of requirements we have now for the branch element, it is obvious that the capacitor is a component of choice, because as higher the frequency gets, as less impedant it is. Second, we can also make a good separation between primary and secondary side, and it's very easy to implement. Let's get now to the rule of thumb for the Y cap. The basic idea here is to compare the voltage drop without cap with the voltage drop with Y cap. The ratio expressed in dB is then the attenuation A we're searching. To get the value of the bridging capacitor, we need now to redraw the known schematics to a simplified electrical equivalent circuit, to which we can then apply Kirchhoff's law. Let's start. First, the circuit without Y cap. I marked here with some green dots, 1 and 2, the points that are interesting for us so that we can better understand how we have redrawn the circuit. If we now apply Kirchhoff's law, then we get the equation for the voltage drop over the listen as shown as V1. Second, let's take a look on the circuit with Y cap. The circuit on the left can be redrawn to the simplified equivalent circuit on the right. As you can see here, helpful to have the green dotted 1 and 2. Again, we take Kirchhoff's law, and then we get the equation for V2, for Vy, and if we put all this together in our equation we have for the attenuation, then we get the attenuation A. This equation is very long and it's very difficult, let's say, to calculate. So I make a small example calculation to see that we can make it a little bit more user-friendly and to go on for the next calculation. As you can see, if we fill in the values here, then we get an attenuation of a linear 0.168. If we now take a closer look to the values that I have highlighted in red, then you can see that they are all nearly 1000 ohms. Some a little bit higher, like 1032, and some a little bit lower, where we have got 820 ohms. The basic equation can now be more simplified if we shorten the red marked values out. If we then calculate it again with the shortened equation, then you can see we have got the linear attenuation of 0.160. That means this is nearly the same. So that we can now use a simplified equation of equation A is zy over zk. With this small equation, we will now do a real example calculation. Here we have got the conducted plot of our power module, a ZIP4 one with 12 volts in, 5 volts out. As you can see, we have already 12 dBs margin to the class B limits. If we now say, let's make a desired attenuation of 15 dB from 4 megahertz to 30 megahertz, then we have first, as a second step, get the coupling capacitance of this power module. This is a screenshot out of the datasheet where you can see that C-ISO, isolation capacitance, has 75 picofarads. This here is a maximum value. This value is measured typically at 100 kilohertz, so we can expect that this value is nearly stable for our consideration. Next step, let us check the coupling capacitance, the stray capacitance from our module, from our device under test to the environment. If we go for a calculation that we say we have got 1 square meter planes with a certain thickness and a distance of 0.4 meters, then we will come up about 22 picofarads as a coupling capacitance. If we go for one conductor parallel over a flat surface, then we will come up with 6 picofarads. As you can see, the difference here is not so big. So we can choose a value between 10 and 20 picofarads. That also fits pretty good with our value we had for the example some slides ago to simplify the equation. So if we put this value in, and if we want to get a desired attenuation of 15 dBs, we first have to make a conversion from dB to a linear value. That means we get 0.177. If we fill this in with our 75 picofarads as a coupling capacitance, then we will see that we come up with 421 picofarads. What is a pretty good close value to 470 picofarads. Let us now check if the calculation is right. Let us make a measurement with a 470 picofarads Y cap and check the plots. As you can see, if we put in a 470 picofarads Y cap, we get nearly 19 dB damping. I make a small value also for 47 picofarads, where we get here 7 dB damping. Please remember, we want to have a damping of 15 dB. We get 19 dB. The expected value of the Y cap was 420 picofarads, so we choose a little bit a bigger one of 470 picofarads. But why is there a difference? The difference here is that CK, the coupling capacitance, is given here with a maximum value. But for this particular power module, if we make a recalculation, then we can see that we will come up with 60 picofarads as in the winding capacitance instead of 75 picofarads. That means less interwinding capacitance, higher damping you will get. What we have done now in the first was we have take a look on the Y cap from its theoretical aspects. So we didn't put into account that there is an inductive component, that we have got on ESR. And I plotted here some values from 22 picofarads up to 470 picofarads from some Y caps and a double logarithmic scale. And you can see that our Y cap we have chosen from 470 picofarads starts with 3 kilo ohm at 100 kilohertz and ends with 10 ohms at 30 megahertz. So this is the range of our conducted plot. Let's check now the behavior of a real capacitor, a real part. Here I get to Red Expert, our online tool, and choose an appropriate Y cap. And as you can see, we have got nearly the same behavior from 100 kilohertz to 30 megahertz. We start with nearly 3 kilo ohm and end with 10 ohms. That means for the rule of thumb here we have, it is pretty good if you use the theoretical value. That means if you only get the equation for XC to make the impedance. What we have calculated up to now for the bridging capacitor was, as I stated out, the ideal equation for XC. If you want to make it a little bit more, let's say, user-friendly and let's say shorten the design time, then we also have predefined EMI filter bags. Here you have all the filter parts in you need to pass the CISPA 32 EMI class B. You have got a small business card in there where you can see the filter schematic. You have got the bill of materials in it. And what you can also do is you can go to Red Expert and can see how the gain and the phase plots are for these filters if you want to try this out for this discrete DC-DC converter. So I hope you enjoyed the webinar. It was a pleasure for me to be here today. I stay here in the line if you have some further questions. For all other topics, if you have some, let's say, questions about power modules, we have a very good support team that you can contact over power modules at weonline.com that gives you a full design in support in terms of, let's say, design in, EMI filter, layout review, and also thermal design support. And this is all free of charge. Thank you.
Thanks a lot, Timo, for your interesting presentation. As you already mentioned, yes, we would like now to turn our attention to your questions. So feel free to enter your questions in the chat so that Timur can answer them.
Yeah, I see one. Does the wire capacitor influence the the radiated emissions as well? How? Yes, of course. The radiation occurs because the current flows over the supply lines. So you have got, let's say, 80 centimeters or a distance that can act as an antenna that can then radiate emissions to the environment. If we shorten this way, that the antenna that you have is within the module, it is much smaller. So yes, it affects. Does this answer the question? I hope so.
I also think so. Maybe one next question. Can I use every high voltage MLCC as a bridging capacitor?
Yes, you can use it. But as I mentioned in the webinar, you have to take attention if you're using it for, let's say, safety isolation, then you have to take a close look if it is a X1 or a X2 capacitor with a safety certification.
Okay, great. Thanks.
Welcome.
Another question. For which isolated power module are the filter bags available?
Oh, that's a pretty good question. The filter bags are available for all our isolated power modules. So for the unregulated, for the regulated ones, for all we have filter bags.
Great. Another question I can see here is why is it so hard to determine the coupling capacitance to the environment?
Because it depends very hard on the environment and how the interaction between the device under test and, let's say, the ground potential or other potentials is, as I showed in the webinar. So I showed you that you can use the equation for two plates with 1 square meter and 0.4 centimeters distance, or you have got a wire over a plate. But it could also be that you have got a pair of wire that is somehow connected to a plate. So it is very, very hard to, let's say, get the real value. This is why I make this example that you can say, okay, if you are roughly in, let's say, tenths of picofarads, then you should be on the right side for the calculation.
Perfect. Thanks. And maybe one
Welcome.
last question. Does the use of a bridging capacitor influence the common mode radiation?
Yes, this question is the same as does the Y capacitor influence the radiated emissions as well? Same answer, yes, of course, because the, let's say, the length or the, let's say, the loop of the radiated of the antenna will be dramatically shortened if you use a Y capacitor, so that the current is not flowing over the supply lines and the load lines over the coupling capacitance back, so that you don't have this radiation.
Perfect. Thanks a lot, Timur, for answering
Welcome.
the questions. I would say if there are any questions left, we will answer them via email afterwards. But for now, thank you very much for your attention, and I hope you enjoyed our presentation. The next presentation will be Advanced Solution Center, the solution to all special and unusual PCBs using the example of stretchable circuit boards. And this session will start at 3 p.m. You can still register, so feel free to join here. And yeah, we wish you a good day and goodbye.
Thank you. Bye.